Hello, everyone. Welcome to a new young session within our Machine Learning Needs Mathematical Optimization Seminar Series. Very pleased to be back with another young session and see so many participants. As always, we're going to have 3 speakers, and all the questions would be asked after and answered after all the presentations. But anyway, if you have any urgent matter or question, you can always put it in the chat. So our first speaker is Buse Guldogus. She's a PhD student in Bahcesehir University, and she's going to talk about pruning in deep learning by optimization. So the floor is yours, Buse. You can share your screen.
Hello again. Thank you for the introduction and for your help, of course. And I would also like to thank to organizers for including us to this series. So I will just share my screen now. Okay. Can you see it?
Yes, perfect.
Okay, then we can start, I think. So today my topic is pruning in deep learning by optimization. It's a collaborative work, of course. I will make an introduction on ensemble methods, ensemble pruning, and then relation with deep learning. Then I will give us our motivation and define our data set and the generation of the ensemble. Then I will give definition of the loss function, and I will talk about proposed methodology. And then I will show my results of the full and pruned ensemble. Then I will talk about a little bit on feature selection and the idea behind it. And then I will show its results and I will be finished. So ensemble methods are highly preferred in machine learning because it combines several models to produce an optimal predictive model. But it comes with computational cost and complexity because it increases due to train and maintain multiple models. So why we use ensemble models? Because it gave us better predictions and more robustness. When I say about robustness, you can see the spread of the data is more smoother with ensemble models. And ensemble pruning tries to reduce this ensemble size before combining all of the members of the ensemble, which leads us to better performance and less computational costs. So the deep learning, we can define it as a neural network 3 or more layers. They are very flexible, but predictions are not consistent because if you change initial settings, the variance will be very high. So a solution to this high variance would be train multiple models and combine their predictions, which is very similar to ensemble methods. So we can use ensemble concept in deep learning models to provide more robustness and reliability. We have two aims in our study. First of it, develop an algorithm to be modeled with sparse optimization, which selects the most suitable deep neural networks while we optimize the accuracy and diversity trade-off by pruning the ensemble of deep neural network architectures. And the second, we use this second-order conic programming model with neural networks as an alternative to other feature selection techniques. So why we use sparse optimization? Because it is highly useful in large-scale optimization problems. It can reconstruct high-dimensional data and increases the performance of the algorithm and the speed of the optimization. And to our research, we couldn't find any model to prune the ensemble of neural networks by using second-order programming, because the literature mainly focuses on semi-definite programming. And we use 3 very known data sets, which are CIFAR10, CIFAR100, and NeEDS. CIFAR10 consists 60,000 color images with 10 classes. It has 50,000 training images and 10,000 testing images. And in CIFAR100 is very similar to CIFAR10, except it has 100 classes, contains 600 images in each. So there are 500 training images and 100 testing images per class. And in NeEDS, it's a database of handwritten digits. It has a training set of 60,000 examples and test set of 10,000 examples. So we created a 300 convolutional neural network ensemble. There isn't any specific reason that we choose 300 because we want it to be deep as possible. So we used our architecture consists of 2 convolution layers, 1 batch normalization layer, 1 rectified linear unit, and 1 pooling layer for each block. And this is randomized between 3 and 5. For each convolution layer, we use convolution filters with a randomized between 32 to 256, with the step size is 32. So we use 2 pooling mechanisms, which are average pooling and maximum pooling, and these are randomly chosen. So the fully connected layer size randomized between 20 to 100 with a step of 10. And we use as a dropout regularization layer percentage from 0 to 0.5 with a step of 0.1. As the learning rate, we randomize with logarithmic sampling, and additional to these, we use Edmond optimizers and sparse categorical cross-entropy loss function. So to define our loss function for pruning, let's suppose that a system consists of n binary classifiers, where classifier I calculates the probability that a selected sample belongs to the first class as fi1. So to find the general result of all classifiers, a weighted majority voting method has been proposed by Polikar in 2009. In this equation, WIs are the weights, which expresses the success of the classifier, but it is just not related with the success of the classifier. It should be also diverse. So the output distribution of PI classifiers are FGT in 0, 1 to show the correct classifications. We can define our loss function of the ensemble in the second equation. We should find the W values to minimize this loss function. In this equation, first term increases the classifier success, while the second term increases the diversity with the Jensen-Shannon entropy function. And the alpha coefficients of both terms corresponds to the provide the trade-off between them. So this loss function will be the base for second-order conic modeling. So we can write this loss function in more closed form as an fx. This is a non-convex quadratic loss function. We also add 0 norm with regularization term. So the 0 norm penalizes the number of non-zero entries of the coefficient vector, and it makes the problem sparse. But it is not a valid norm because it is very difficult to solve problems with non-convex expressions, and these problems are known as NP-hard problems. We made some convex relaxations for non-convex expressions, and at the end, we transformed the second-order conic programming model. So in this equation, we add an additional term, which is T, equals the X transpose QX. And then L came from the Cholesky factorization, where Q equals to L multiplied by its transpose to adapt this non-convex quadratic loss function to second-order comp programming. So the important thing is to get accuracy values which are very close to unpruned full ensemble model. So in the first table, you can see the test accuracies, models, and thresholds. You can see that in CFAR time we pruned from 300 models to 56 models, and we almost get similar test accuracies, which is very same for the CFAR 100 and MNIST. On the last table, you can see maximum score, average score, and minimum score with number of models for pruned ensemble and full ensemble. We can say that even though we prune the ensemble, we still get the better accuracy or very similar accuracy. So that's a very good thing because we try to reduce the complexity of the model. So we achieve that. So if I go back to the feature selection makes your problem more accurate. So it increases your prediction power by selecting the most critical variables and eliminates redundant ones. So there are two main types of feature selection techniques, which are supervised and unsupervised. And supervised method may be divided into 3 methods, which are wrapper, filter, and interesting. But we don't know what is the best feature selection method, right? So we want to discover which one will be the best. So we have to make systematic experimentation to find out which one will be the best for our specific problem. So the idea is really similar to ensemble pruning techniques. We consider all possible members and then remove redundant ones. So we created a really basic neural network which consists one input, one hidden layer, and one output layer. We used Adam optimizer with binary cross entropy loss function. So to summarize this technique, we have actual feature set, and we train each feature on this basic neural network. So we create an ensemble from selected features, and then prune the ensemble with second-order comprogramming. Then we train the selected feature on the same neural network and get the performance of prune models. And on the right side, you can see our data sets, types, feature numbers, instances, and classes. And all of these feature techniques can be found in the link below. So on the right side, you can see our data sets, and on the left side, you can see all of these feature selection techniques. We compare our method, which is the last one on the table, with 19 feature selection techniques, and we found out that our selection techniques works best in long data set and base hook data set. So we can say that also, I have to note that feature selection with second-order comprogramming is really fast when you have a lot of features. So it's a good alternative to try and look for other feature selection techniques. And that's all. Thank you for your time. If you have further questions, you can always get in touch.
Thank you so much, Buse. It was a really interesting talk. So our next, thank you. So our next speaker is Sherly Alfonso Sanchez. She's a PhD student in Western University and an auxiliary professor at Universidad Nacional de Colombia. And she's going to talk about credit limit adjustment using reinforcement learning. So all yours, Sherly.
Thank you, Miren. Hi, everyone. I'm going to share my screen. Please let me know if you could see it.
Yes, I can see it.
Okay. Thank you for the introduction and for the space to share our research ideas. This is a work that has been done during my PhD and supervised by Christian Bravo Roman and Dr. Christian Sendova, also with the collaboration of Rappi company. During this talk, I am going to first give an overall view of the data provider company, to then follow with the research questions, how this problem was formulated as a reinforcement learning problem. And finally, I'm going to show to you some experiments and the final results that we have obtained. And I'm going to conclude with the deployment and some final ideas. So overall, the data provider company was Rappi. This is the first Latin America super app that started as an intermediary among the customers through their application. They have different kinds of demands of products, and the application connects the customers with different kind of couriers. Because of its vast success, they also started to offer products in financial services. Mainly, they have recently launched a credit card, and there it appears our problem that was how to decide which customer of this Rappi card should receive an increase in their credit limits. This is because they have followed a high volume, low amount strategy. That means that they aim to conquer unbanked population. This is people that usually don't have credit history, but given to them a low amount in their credit limit. So they want to change progressively those limits. And with this problem in mind, we have these research questions. The first one was if this question could be resolved using reinforcement learning techniques. This is to create and automate and periodically generate an optimal policy. This is a recommendation, and also to evaluate if the alternative data that they have that are given because of the usage with the Rappi application could be improve the performance of our models. These models were used to train the reinforcement learning algorithm. After that, we aim to compare the policy that we generated using reinforcement learning with baseline strategies, which were selecting randomly the increments or increasing to every customer or maintaining to all. This is because until this moment, they had an ad-hoc strategy, and because of that, we could not compare with their current policy. And finally, how should this strategy should be deployed? Overall, a reinforcement learning formulation is a sequential decision-making problem in which in every step, an agent will perceive a state, and given this state, the agent will perform an action. This action will interact with the environment, and it will produce a feedback signal. And after this final signal, it will transit to a new state. This kind of learning is different from supervised and unsupervised learning because here we don't have a target variable, but instead we have to optimize this total future expected reward. So for mathematically, this is a Markov decision process in which we thought every step as the decision that we need to make for the end customer. And in this part, this is an episodic problem where the number of steps is equal to the total number of customers in the portfolio. And we define the reward in the step n as the advantage given for the action to increase in comparison with the action maintaining if the action is increased, or 0 if the action is maintained. And we aim to maximize the total expected future reward, where gamma is the discount factor for all the customers in our portfolio. This is a very challenging problem because it's different from having a deterministic environment, since we are not going to be able to perceive immediate rewards, and also we needed to decide the periodicity of taking these actions. Since this was decided also with the company, we decided periodicity of every 3 months. And because of that, we needed to construct an environment simulator that was based on decision history during the last 6 months. Here I present the elements of the reinforcement learning approach. Here we have the states, which includes customer features of the last 3 months. We analyzed the facts included only financial variables, and also including global variables that are given because of the usage with the Rappi app. And also we included another variable that accounts for the global state of the company in terms of provisions. Having this formulation, we needed to construct a simulator that takes into account the default probability, and also we constructed a 2-stage model in order to make predictions about the outstanding balance after 3 months after taking the action. And the reward was thought as the expected profit using not only the revenue, but also the provisions of the portfolio. So overall, we have these 3 first months, the information of the customers, we are going to take the actions, and after 3 months, we are going to evaluate the impact of those actions. And our reward function here in more detail, we have the balance among the revenue. Here we have the revenue that is given because of the action. This is the outstanding balance that is predicted. And here we have the probability of not falling in default minus the provision, where the provision takes into account not only the probability of default, but the loss given default, and the exposure at default. Here for the exposure at default, we needed to calculate the credit conversion factor, which is the expected amount in excess of the current outstanding balance that we expect that a potential defaulter will have. And after that, we needed to mesh all of these formulations and to construct the simulator environment. After several experimentations, we found that the best model will be a two-stage model where first we have a classifier about the outstanding balance type, and then it proceeds with a regressor model that will have the amount of the balance at the end. All of these models were trained using not only the financial variables, but also the alternative information, that is information that usually traditional banking sector don't have. So we wanted to see if this information will be important for them. After that, like an oral, we are assuming that the customers will behave as in the past. We are learning from that experiences, and we construct that simulator. And after that, we define the states of our reinforcement learning algorithm as this tuple, where we have different variables. The first one is the monthly average utilization rate. Also, we consider the monthly average payment rate, the consumption rate, the number of non-payments during the last 3 months, the current credit limit, the interest, the monthly interest rate, and also the change in the provisions after the end decision. This was because we wanted to apply traditional reinforcement learning, which needs discretization. So after defining these variables, we perform certain discretization, and we employ double Q learning algorithm to learn this policy. We employ this in contrast with the vanilla Q learning because of the maximization bias that is well known with the vanilla version. In this case, we are going to produce 2 tables, and in every step, we are going to update every one of them. The selection is done using a Bernoulli distribution with the probability equal to 0.5, and we are going to update using the Bellman equation. But here we are going to use another table, Q2, that is used to face the problem of overestimation. Here we have alpha as the learning rate, gamma the discount factor, and star represents the better action that will be taken into account Q1. Here I am going to present some of the experiments and results. For the classifier, we defined 3 different classes. For the customer, class 0, which represent customers that had small to medium balances. Class 1 that has greater balances. We identify 1 threshold for defining these greater balances. And the class 2 were inactive or full payer customers. We found these results in terms of weighted F1 score using only financial predictors and adding the alternative information. After that, we conditioned over the class of outstanding balance and found that for the class 0, the best model was an XG boosting, and for class 1, the best model was a random forest. We evaluate using root mean square error and also weighted absolute percentage error, and we found that including this alternative information does not bring an important predictive power in these models. So we proceed using only financial features. So we trained these models, and then our objective was to train the reinforcement learning algorithm. For that, also we need to calculate the credit conversion factor of the portfolio, and that was done using the individual CCF factors as the mean of those values, And also we perform a hyperparameter search of the hyperparameters of the reinforcement learning algorithm, namely for the we tune epsilon, which represent the trade-off between exploration and exploitation in these numbers, and also for the alpha parameter, which is our learning rate. Here I present some of the results. This is the learning process that we obtain using alpha equal 0.1, and this is using 0.010001. And then we could see that here is better the performance, and because of that hyperparameter search, we proceed with epsilon equal to 0.1 and alpha equal 0.001. Finally, using these hyperparameters, we train the double Q learning with more episodes, with 300 episodes. And also, we permute the rows of the data to avoid any bias that could be done having fixed the order of our customers. So we permuted the rows, and this is the row learning process for the 3,000 episodes. And here is the smoothen that represents the average every 10 episodes of our algorithm. Sorry. Here is the comparison between our strategy and the baselines that we define at the beginning of our research questions. Here you could see that is our algorithm outperforms to maintain to all the customers, or here increasing to all the customers, that is the worst, and increasing randomly to the customers. And after that, after training our algorithm, we need to decide what is the recommendation policy, what is the generated policy. For that, we took one of the Q tables. This should be invariant for every table, and generate recommendation for each of the customers. We found that in this case, 19% of the portfolio receives recommendation of increasing a beta factor with respect to the current credit limit at that moment. And here there are some histograms of the states in which the recommendation is increased. We could observe that here our agent, this is the discretization that we done, and this is the number of recommendations. So we could see that here our agent rarely recommends increase to customers that are not using the credit card. Here are customers that has had utilization rate less than 5%, and mostly it recommends to give to customers that has had between 20 to 40%. And in terms of the payment rate, we could see that our agent recommends to customers that has had at least 35% of payment rate, and also mostly that has had above 90% of payment rate. This could be understood as expecting that when you increase the credit limit, your customers that are full payers will transit from being fully payers to be debtors in the future. In terms of the consumption rate, we have that our agent recommends increasement to customer that has consumption rate from 30% to 50%, and mostly that has had above 90%. And in terms of the current credit limit, the greater the credit limit, the less likely to receive an increasement. And in terms of the number of non-payments, we could see that our agent rarely will recommend to increase to customer that has had 2 no payments in the last 3 months. And that instead that the consumer will be up to date, and also that the consumers will have had a higher interest rate. So it will. This is because we are taking into account in the reward, the revenue part. And in terms of the state of the global state of the company, we observe that the agent starts to increase almost uniformly until arriving until 40% of the total possible amount of provision of change in provisions, and then it starts to decrease to be more strict in the increasements. And finally, it ends until giving at most 46% of the total available provisions. Here we presented like the overall view of our proposal of methodology. We have here the last semester of information.
2 minutes, Sherly.
Okay, thank you. I am going to finish. Okay, we have the last 6 semester of information. With this information, we create the simulator, and based on that, we train our reinforcement algorithm that will produce the output to give the recommendation system. Those will give new experiences that will enhance the construction of the simulator for the next stage. So as conclusions, we found that it's possible to solve this question using reinforcement learning techniques. We, in contrast with other studies, we take into account not only the revenue, but also the provisions using the CCF factor calculation. We found that the information about alternative variables is not very significant in this case. So this methodology could be also applied for traditional banking sector. And finally, doing adequate hyperparameter search, we could be able to outperform the generative policies. All this work was done using Compute Canada resources. And thank you so much for your time. If you have any question, I'm happy to answer to you.
Thank you so much, Sherly. That was really interesting, really nice. So we'll continue, and then if someone has a question, they can ask at the end of all the 3. So our last speaker is Adrián Carrasco Revilla. He's a data scientist senior at Inetum, and he's going to give a talk about building replicable models for energy grid management, a graph approach from RENergetic. So all yours, Adrián, you can share your screen. Adrián, can you hear me? Yes. Don't forget to unmute yourself because, yeah. Yes.
Now,
perfect.
now you can hear me, right?
Yeah.
Sorry, I was talking to myself. Okay, so let me go.
Yes, perfect.
Okay, thank you. Well, I will start the presentation right now. First of all, thank you so much for having me. It's a pleasure to be here. I will be talking about building replicable models for energy grid management, which is an approach that we've taken within the RENergetic project. But before we go to that, let me just quickly introduce myself. I'm Adrián Carrasco Revilla. I'm an industrial engineer with a master's degree in mathematics. So I ask you for your forgiveness because I've seen that you've all used probably LaTeX to create a presentation, but I am now in the world where I'm more comfortable dealing with PowerPoint than with LaTeX. I know it's a shame, but it had to happen at one point. I'm a data scientist at Inetum, Spain. NLP and time series development are my main 2 areas of research. And just to give a round figure of who I am, and I made this presentation listening to the album Hamilton and the Mexican Grand Prix. So we're going to talk about a bit the recommendation problem that is presented in RENergetic in the project that I'm currently working on. show some of the basic workflow that we have created to use the graph-based solution implemented currently, and also lay some foundations for future work, which will depend on the amount of experimentation that we're allowed to do on sites. So first things first, I wanted to start by talking a bit about what is RENergetic, what is it that we do. So RENergetic is an European Commission funded project which tries to give energy islands the power to control their consumption and production of energy, focusing mainly on renewability and the ability to use and consume renewable energy at the most efficient level. We are mainly we have mainly four areas of work, or four main considerations. The energy governance, trying to give the citizens the control over the power that they produce and consume, as I explained before. Also, it's very important, the social interaction. We want people to actually be part of this effort, because it is the feeling that we have that sometimes the way we commute with the renewable energy is a bit farther away from our actual day-to-day basis, and we want people to feel like they are participating in the process of transforming their life from fossil fuels to energy systems, renewable energy systems. Also, it is important for us to increase the attractiveness of renewable sources and the control that they offer, the possibilities that they allow, not just for climate reasons, but also from a business standpoint. And finally, and I think this is the most important of all for us, is the replicability. We are currently working in three main sites. We're working in Poznan in Poland. We're working in Segrate municipality in Milan, Italy. And we're also working in NeEDS in Ghent in Belgium. These three sites are working with some of these cases of use that I'm laying out right here: building electricity demand response, supply optimization, EV charging, heat demand response, supply optimization. So not all of them are working on all, but they allow us to have a global view of the whole problem and how to generate solutions that tackle them. But it's very, very important that the solutions that we create are not only useful for the projects that belong to RENergetic, but also that we encourage the rest of in this case of the world, to generate these visions of the energy islands, to give this power to communities to be able to use the same resources that we are creating. Now, for the presentation today, I will be focusing mainly on one of the issues that we're currently tackling, which has to do with heat demand response. In other ways, we are trying to lower the consumption of non-renewable heat sources by focusing on giving instructions or acting on the behavior of the assets that we have control over. So one of the things that we're working on is what we call heat demand manual response. This has to do mostly with the recommendation of actions to be taken by the user. This is one of the examples that we're looking at, with the generation on one side, the conditions that we have of the campus, or because we're working mainly with the university buildings, university residencies, the conditions outside of the buildings, and we define the figure of the presence of the energy manager as the one to take charge of all of this, to fix the threshold of renewability or the renewable energy that comes in and out, and make a recommendation of the temperature that building or that room should have to reduce the amount of non-renewable energy that is being used currently by the system, but the energy island as a whole. Now, this is a very complex problem, and the end goal would be to have it almost automated, to have some notions of how the temperature reflects on the on how comfortable people are living within the buildings, which is also part of the social interaction is also based on whether these tools that we are providing actually allow the people to maintain the level of comfort while reducing the amount of energy that they use. This is something that is going to become more and more important, especially now that the winter comes in. And so the results of these first tests, as we start developing and we start building and putting this into production, are going to be very, very helpful, both for us as technical developers, but also for the social scientists working in the project that are looking to draw some interesting conclusions from this. So in order to solve this problem, we define sort of a checklist of things that we have to solve in order to be able to solve this problem accurately. First of all is we define the calculation of the renewability of that percentage of renewable that each asset, its consuming asset, is using at the moment. Evaluate which assets are better or more fit to handle the recommendation of lowering their consumption. And as I said before, also very important, building a replicable and changeable package. We understand that most of the assets that we're considering right now are going to be changed in the future, going to evolve. For instance, we're going to see some examples of the energy layout that we have at the moment, and how we hope that they are going to change and translate into more renewable in the future. So, okay, going for this first task of calculating the renewability of the system, mainly how much renewable energy is being produced and consumed by the energy island, we are focusing mainly on this structure for assets and the classification. Now, this may seem fairly simple, but it requires a lot of determination or standardization by our side to make sure that any new energy communities that come in could easily understand this and use them for their own systems. So we have also the generation, the consumption, and the grid. For the generation, it's the only one that we have like two sides, renewable and non-renewable. There's a third category that it's kind of like a mixed renewability, because we have encountered some energy assets, for instance, heat pumps that have a mixed conditions, almost like a hybrid condition in the energy that they produce. So they may be renewable at one point and non-renewable at another point. That is something that we have to take into consideration when talking about the renewability. But we will be focusing mainly, and I draw that little battery with the red icon there to let you know that we will be focusing mostly on consumption, because this is where the recommendations will be sent. We understand that there is little to no effect that can be done in the production of renewable sources, thinking of solar panels. So the energy that they produce is the energy that they produce, but also it could be also feasible to apply this to generation in order to store energy in batteries that then can be used later on when maybe the production of renewable energy is expected not to be that high. So this is the first layout that we find in our test. We have two main buildings they are campuses buildings, each of them with their own consumption, and we have two gas boilers which are fully non-renewable, and of course a solar collector that produce hot water, which is fully renewable. And you can see the layout of this grid in such a way. Now, the first decision that we decided to do was to make this a representation of a graph instance. The reason for this was because we wanted to tackle the first issue that came to mind, which was, okay, we have the values of the energy production and consumption but we don't know how that production and consumption is being shared between campuses buildings. And we need to know that if we are going to give a more, let's say, precise or specific recommendation to the assets. So this will be the graph that we're looking for. We have the nodes which, or the vertices which relate to assets, to energy assets, whether they are consumption or production. We have the edges, which are the connections, and the weights are the value of each of these vertices and edges. For instance, I put an example there of annotation that we're going to use going forward, which is that the weight of that edge is the basically the energy that is being shared between asset J to asset K. With all this, it's fairly easy to define the system of equations that we need to solve in order to know all the information to calculate the renewability, because we want to know for each asset on the right. I haven't named this, but just so that you it is easier for you to understand. The assets are named from the up, down, and left to right. So it would be this would be 1, 2, 3, 4, 5. And as we have some renewable and non-renewable, we want to know how much share of each are they sharing. This blue dot here is the grid elements that we use to stabilize the balance of energy, as we understand that we are connected to the grid, and therefore not all the energy produced will go to the assets. Not all the energy that is consumed by the assets could come from the energy produced. Now, the issue here is that this system of equations works only for this element. If there is a change in the grid, a new asset in any shape or form, now the number of equations are going to change. The equations themselves are going to change. If there's a change of connection, it's impossible to reflect it other than changing the code that generates these equations. So as we were delving into the use of graph theory, it was pretty simple to just move to the use of the matrices that come from graph theory specifically. Now that B there is the incidence matrix from any given graph, and defining these allows us to have the equations into a way that was easily extractable from the graph system. Now, because of this, this means that the grid could change, and as long as we can retrieve the graph form from it, we can derive the system of equations. Now, you may all be thinking the same thing that I was thinking when I started working with this, which was that this problem relates to whether it's feasible or not to solve that system of equations is going to come down to the number of edges and the number of nodes within the graph. Now, because of this, in the end, you arrive to the conclusion that because you need to have the same number of edges and the same number of edges and nodes in order to be able to solve the equation, that you need that for each system you have a one-to-one direct link in order to give that. Now, for instance, there are some of the cases in which the system could be feasible, which is to separate the graph into what we call feasible components. The idea of this is to have as much specific information of how the energy is shared between all the systems based on both the connectivity between the assets. So you can see here, for instance, that this is usually a bipartite graph, meaning that you have two big components which are connected one to the other. But also you have two separate components which shown are bipartite in nature, not taking into account, of course, the grid element which connects them all. But we can define those two components as different feasible components in trying to draw the share of energy based on them. That way, the system should be able to separate the equations based on this layout and produce the outcome of the system. Now, for instance, in this case, we will have a conditional solvable because there is one way in which the system could give the energy and could obtain the levels of energy to be shared between one another, but there's another one that cannot. And of course, for the second component is always solvable, as we will always have the same number of edges as we will have the number of nodes. So that way, it is easy for us to translate from one to the other. Finally, and I will be quick about this because I'm guessing that I'm running short on time. With the recommendation system, so at the moment, what we have is we have the supply and the consumption calculating, and also we have the renewability score. Now with that, we want to create the recommendation algorithm that allows us to say which of the assets needs to be warned or needs to be recommended to lower their temperature, or to decrease, in the end, to decrease their consumption. Now for this, we wanted to create a weighted recommendation based on several things. First of all, of course, the renewability score that we calculated before, the representative consumption, meaning the amount, that asset, how much percentage of the consumption is on the total energy island, and also the representative forecast, meaning how close the forecast has come to the actual values. If there is a big deviation, if it's an outlier, for instance, to be signaled out as that is the issue, and that may be the action that requires lowering the consumption because they are consuming more than expected. Now, with all of that, with a weighted average, we can get the final recommendation. The reason for this division of the scoring and this almost statistical approach to it, it's to be able to signal those assets that consume more energy within our energy island. Also, to, let's say, benefit from those who have a more regular consumption and are less prone to big spikes of energy, and also to signal the assets with less share of renewable energy. All of this is customizable by the energy manager, which allows him or her or there to be able to shift the recommendation to be more flexible to things that are outside of the scope of the algorithm.
1 minute, Adrián.
Okay. So basically what we have is we are going to extract the information at the moment from the site of the layout of the energy grid. At the moment, we are working on extracting the real data that we're working on, but we are simulating data based on previous behavior, and also on the structure of normal energy time series. We're doing the forecasting, the renewability, and sending the recommendation to the correct assets. This is an example of one of the models that we are working on. And based on this, we have the layout of the time series. It's still using it's still like it started training not so long ago. So this is only with 2 weeks time prediction. But when we're using a multi-level time series training model, we are getting closer to the real results. In future works, we're looking for using the grid, the graph model in reverse. So at the moment, we're looking at the consumption and trying to see the renewability. We're trying to look at if we predict the level of consumption that is going to be, how can we planify the assets of non-renewable assets? And also, and this is most important of all, using the information that we get from the social experiments to try to have reinforcement learning with the scoring that we have to be able to say, okay, this is the best time to make the recommendation. And also using causal inference models to be able to give an accurate or somewhat accurate estimation of why this is the best moment to make the recommendations, which allows us to know more about the grid and the people itself. Thank you so much for your attention. Sorry that I had to go a bit quick at the end, but hopefully, if any have any questions, please feel free to ask, and I will gladly respond to the best of my knowledge.
Thank you so much. That was great. It was a really nice and interesting presentation. So now we open the floor for questions from the audience. So if you have any question, you just can raise your hand or write in the chat, and we'll give you the rights and the permission to use the microphone and the camera. So if anyone has any questions, feel free to ask. Any question for any of the three? Yeah, one moment. Yes. Arno, you can unmute yourself.
Oh, I'm sorry. I was talking to myself. I was asking how which techniques Adrian used to train the model. Like, was that using reinforcement learning, or like which?
You mean to train the time series forecasting model?
Yes.
So in order to train the model, we have a structure which is composed of 3 models that are both competing against each other at the beginning and then being merged together into one final model. So we have a shapelet discovery model. And the outcome of this model, based on the previous iterations of the time series, is sort of the shape of the time series for the next day. The second model works more as a normal regression model, kind of like an ARIMA model, but more into the deep neural network works of like LTSM and so on. Yeah. And the third model, it's we call it time series components. Is similar to Prophet or GradGuide. This is some of the libraries that we're using to make the predictions, and is based on Fourier decomposition of the time series on trend seasonalities. So the idea is that all of those models produce different types of outcomes that are both competing against each other, because all of them produce a final value for the time series of the next day. But also, when we have enough data and the models are stable enough, we can use those predictions as part of a bigger model that combines them all. So that's sort of like the strategy that we follow to make the forecasting.
So you combine like 3 models into one big graph network that then makes the final decision or prediction.
Yeah, precisely.
So not that you would like compare the 3 outcomes of the 3 models with some formula. You actually use a network to do that. Okay, thank you very much.
Thank you. Any more questions from the audience? If there are no more questions, then we'll just close the session. Thank you so much all for coming, and we will be back as always next Monday.
Thank you, everyone. Thank you so much. Pleasure.
Thank you very much, everybody. Thank you so much. It was very nice.
Very nice presentations to both of the 3 of us, 3 of you. Thank you.
Thank you so much.